Oh, yeah, it definitely helps, yeah.
Thank you.
Couldn't get. I got some answers. I feel like I have to redo half of that now. So, for the purpose of today's class, we are going over something called the power quality. And I'm struggling with. Okay, power quality. Yeah, this might work. Let's have some fun. So for today's class and for what's happening on Wednesday, there are a lot of stuff that I'm just going to give you notes. I hope you guys write it because they're on the off chance that I want to ask a 3-point, 2-point question on a midterm. It's just going to pop at you. The crux of this class comes on Wednesday when I'm going to do some number problems. And those number problems are what is going to drive your homeworks. Homework 2. And homework 2, just to circle back, homework 2 is 2 weeks from today. And the reason why it's 2 weeks from today, there is a software that you guys need to pick up. It's called Powerball. It's mentioned in the homework. It's a free software. You just download it and watch a bunch of YouTube videos on how to handle it. Essentially, you are just going to draw lines similar to what I'm doing on a one line, and you hit a start or a play, and it just gives you how the power is flowing. So if you have a reactive power, is it flowing backwards or is it flowing into the load? It just comes up with a bunch of arrows and whatnot. So don't wait until week 4 to week 3 end to start your homework. I think you should start looking into Powerball immediately, like start it tomorrow or this week and get it out of the way. The number problem should be pretty simple. Most of you guys are going to get it. My issue is you guys might struggle with Powerball, and that is like, oh, never saw that. I'm not sure whether it's part of this class. You will either struggle with Powerball during my homework or you're going to struggle during the labs. I wish you guys struggle during the labs because then when you come to my homework, then I'm like, yeah, you guys know how to do it. But it's either one. This power quality stuff is required for your lab 2. So if you have already caught up with lab 1, for lab 2, power quality lecture is really going to help you. As far as slides were concerned, I will have slides for, most likely I'll have slides for Wednesday. That's more to help you understand this lecture. It's not a substitute to this lecture. So if you're not taking notes, if you feel like, nah, I have some notes lying around, I'm just going to manage with it, that's up to you. And also, one quick update on the slides. Those slides, I make it and I haven't vetted it, I haven't sent it to the department to take a look at it. It's just that I feel like that's helping me drive the lecture. So you're going to get it only as an email. It's not like free for all, take it, do it, whatever. It's your individual stuff. What you do with it, I can't control, but at the same time, I want you to maintain it within the school. Similar to the lace or ruffles that I had, I was like, what was I thinking? So anyways, so you will have some slides. Again, it's not going to be super helpful on the exam, but it will help you understand what this lecture is all about. All right. So far, we have seen this. This is the instantaneous power. And there were a bunch of assumptions that we did. One was with regard to how we define V of t. And just to jog your memory, this is instantaneous power. This is instantaneous voltage. So Vm, let's go with cos or sine. Yeah, let's go with cos, cosine, omega t, or Vm cos 2 pi f t. So power quality, essentially what power quality means is it's actually a study of the quality of voltage. Current does play a part, but overall any power quality engineer that you talk to, and there are engineers who are called power quality engineers, it's essentially a study of the quality of voltage. They are so concerned about the voltage. Anytime there is a flicker, we have an engineer at PG, and the reason I'm mentioning that is he used to be a power student here, did distribution engineering for a while, and then got fed up dealing with customer issues, and he said, you know what, I'm just going to become the next power quality guy and deal just with the customer issue. So spends a lot of time just looking at voltages and figuring out ways and means to improve our voltage.
Nice.
So it's a study of voltage, and the qualifications for the study are basically qualification. You have three. One, of course, is the magnitude. No, one, of course, is this waveform itself. So we are more comfortable after seeing one phase and three phase, or single phase and three phase of a sinusoidal wave. What happens if you have a non-sinusoidal wave? Frequency. What happens if you have a frequency that is not 60 hertz? And of course, 50 hertz for countries that are on 50 hertz. In other words, what happens if you don't have your frequency as your fundamental frequency? And the last is the magnitude of the voltage. Well, what I mean here is, instead of 120 volt on your receptacle, if you are getting 150 volt from PG, that's a big issue, and that shouldn't be happening. So this lecture is essentially, we just come up with a few things and we say how distorted the voltage or how distorted the current is. So this guy is good, this guy not so good. Essentially, that's what I'm trying to say. So there are four different, four different classifications. Yeah, four different studies, I would say. First one is a transient. So this transient guy, transient typically happens when a breaker opens or closes. If there is an event that has happened, like you have just lost power and then I'm bringing back the power, immediately that's a transient power, and we need to be careful about the quality of power that I'm sending across. And what I mean by quality of power are these three things. I need to make sure that I'm still giving you 120 volt at this point. I need to make sure that the frequency is 60 hertz, and I need to make that I'm sending you a sinusoidal wave. Chances are, for the first few cycles, we may not be able to do that. And there are ways and means to suppress that. So quick question before I lose you on note taking. When I say a cycle, how many milliseconds would be one cycle for us? Yeah, someone said that.
That's 60 hertz.
60 hertz, but how many milliseconds?
60,000.
Yeah.
1 second? No.
60,000, right? milliseconds.
60 milliseconds?
So keep this in mind, again, not part of this lecture, but it's nice to know and will really save you when you're trying to visualize this thing.
Yeah, 60.
Yeah.
This is pretty useless in our industry. You can take it for electromagnetism and give it to them and they'll be pretty happy. For me, this doesn't make any sense. For me, I have to do this 1/60 and get the time, and that's 16 milliseconds.
Nice.
So the only reason you guys are not seeing any of this jazz is because in 5 or 6 cycles, I am able to provide a good power to you. But for the first 5 cycles or so, it would be rubbish. And it's still in milliseconds, so your device is not picking it up. Worst case, you see a flicker, and that's even several milliseconds. So there is an operation that we do, breaker open and close. We shout at folks if it's 0.5 seconds or above. So that's how quickly things happen for us. And you guys don't get it. Or as a customer, you will see. And if there are several things that we need to coordinate, the power utilities in the US, they depend on GPS, and that's how we coordinate our clocks. So every substation literally has an atomic clock. You can pretty much go and put your watch against it and you'll see that even your Apple Watch is a bit behind, or sometimes it's a bit faster, but we run it using an atomic clock. So using atomic clock, we are talking to different substations and figuring out which breaker to open, what needs to happen at what time period and what not. But 16 milliseconds, keep this in mind. That's literally your one cycle. So the time it takes for one VFT or IFT to go through, so it's 16 milliseconds. And of course, you could say that there is an impulse transient or an oscillatory transient. Worst case, I might ask, what are the 3 qualifications? What are the 4 different studies that we look at, or 4 different stuff that we need to know? Sorry, you had a question? Did you have a question, Dave?
I was just wondering, what are the qualifications for it?
What are the qualifications for what?
Like, what is it for?
Oh, so these are the qualifications for power quality. When we talk about power quality, we are looking at these 3 things. At the minimum, I'm talking about, hey, am I giving a sinusoidal wave? Is my frequency at 60 Hertz? Is my magnitude the agreed voltage? So the problem that you did is 480 volts. Here I'm just talking about the resistance. Is that clear?
Do both of those words say transient?
Yeah.
Okay.
Can you even pull it up a little bit?
I think I should start my notes somewhere here. So we talked about the transient. The second one would be short-term voltage variations. Third would be long duration. Steven, good. And the fourth would be anything that doesn't fall in these 3 categories, we just put in the 4th category. So both short and long term have interruptions. The thing here is with short term interruption, I'm talking about a voltage loss of like it's 0.1 per unit. And I have to tell you what a per unit is. We have an entire lecture dedicated to this, but keep in mind, and I'll explain it in a broad 30,000 view of what a per unit is. So PU, because you're seeing it for the first time, let's just write it as per unit. The way that I like to think of per unit is, any item, just pick, I don't know, a laptop. The cost of laptop, if I say, is the price of maybe like 500 times the price of GI89 or 10,000 times the price of this guy, it doesn't give me a whole lot of info, because then I'm like, okay, what is the price of this? And what is the price of this? So what per unit does is, let's get out of these arbitrary numbers and bring it to one particular unit of measuring. In US, what we use is US dollar. If you go to Europe, there are like 3 or 4 currencies. British pound, Swiss franc is still around, and then euro. Probably there's a 4th one or 5th one. Do you know if France is completely euro or?
Fully euro.
Is it fully euro? I know Swiss is still Swiss franc. So think about going to a supermarket in Europe and you see, especially in Switzerland, you're going to see price, and depending on what part of Switzerland you go, you're going to see price both in Swiss franc and in euro. Fortunately, Swiss franc is closer to USD, so you'll make it out. Used to be less, then it came up, and now it's almost, yeah. Anyways, rather than dealing with all this jazz where I say that, hey, Pacifico operates their system at 13 kV, PG operates at 12.48 kV. What we have decided is we will come up with one unit or one voltage for the entire system, and we are going to define everything else based on that. So how you define your per unit is a lecture by itself, we'll come to that. And there are certain ways that we say that, A, if there are 18 students, I want to see 18 different per units, because that's your system. But at the end of the day, you will just give up and figure out, okay, there is just one better way of doing it, and you'll just go with that. But for the time being, I'm going to say that, interruptions, short-term interruptions, which are like 0.1 PU. And what I'm trying to define is, we are going to define a single way to come up with all the voltages and currents and whatnot. It will just be one single currency that we are going to use across the system. Then there are SAGs, which is 0.1 volt less than E less than 0.9. PU. And there are swells. Swell is 1.9.
How do you say the last one?
Oh yeah, swells, SWELL. Or is it just one L? I think it's double L. So let's take a voltage that's pretty common to this part of the river, which is 12.47 kilovolts. That's your distribution line voltage. I haven't said anything else, so is this line to line or phase voltage? If I just give you 12.47 kV. Thank you. So this is a distribution voltage. What this is telling me is a sag happens when my voltage is between 0.1, 12.47 kV, or 0.9, 12.47 kV. Now I haven't defined the PU yet, but imagine if my PU in my system I say, hey, 12.4 kV is going to be given number 1, like just physically number 1. In which case this is 0.1 times 1, which is 0.1, 0.9 times 1, which is 0.9. So if your voltage is between 0.1 or 10% to 90% of the actual voltage, you're going to have a sag. The sag typically happens when a lot of load comes into the distribution all of a sudden. So imagine everyone was driving a Tesla and all of them plug in their Teslas at the same time. I cannot suppose this is 12.47. It is going to fall. Like the voltage will drop. Like I just don't have enough power to push through. The swell, on the other hand, is kind of crazy. That happens when there's like too many generators come up and start pushing power through a distribution line. Safe to say, even with this, we have ways and methods to make sure that you guys get your 120 volt, but there is a lot of stuff that's happening in between. So sag is when you are operating less than the assigned voltage. Swell is when you are operating more than the assigned voltage. Truth be told, if you are doing 1.8, we'd rather shut down the system and figure out what's happening.
So in an interruption, there would be 0 voltage, right? That implies it's disconnected or turned on.
So
Short-term
short-term voltage variations. Short-term voltage variations are kind of crazy because we need to actually take care of this, but at some times it happens. Where was it? It's 16 milliseconds, right? I think I used a very strong pen today. Give me a second. So imagine this. You have a 3-phase line and a short tree branch just falls on that. We do not want to be in a situation where we are taking down thousands of customers for no good reason. So a short-term duration is you had a fall, but it sort of cleared away by itself. But for that particular moment, there was a voltage drop because 2 lines shorted or there was a voltage collapse. So if a tree or a branch falls on one of the lines, there would be a short-time duration. You'll probably see some sort of flicker, but that's about it. Long-time duration is when a branch or tree falls on 2 lines and it's there, it's just there. And or a bird or squirrel finds some way to, sit between 2 lines and it's just there. And then that's a long-term duration that you have to, there's no other way. It's a proper shutdown.
It's short term if it's less than the 16 milliseconds? What
No,
period?
it's like 5 to 6.
So less than.
And again, it depends on the customer. So some customers value the equipment so much that they're like, no, absolutely not. We have an handshake, not a handshake, we have an agreement on what would be considered. What is acceptable to the customer and what is not. Which is why when, and I didn't know this, the point of separation for PG and your house is at the meter. What you do inside, we don't come into your house and say, oh, the receptacle is gone, or the TV is, hey, this was rated for 55 inch, you now have an 80-inch giant screen, can't help you. Because we can control things only up to the meter. After that, it's beyond us, we just can't do it. Similarly, for large customer, there would be a point where we say, we just can't help you beyond that. I deal a lot with solar fields right now, and all the solar folks, the point where we sort of do a handshake is at the substation. Sometimes even beyond that. But at the substation, if you give me these 4 things, I can assure you that the power quality is going to be so and so. And how we ensure that is we tell them what equipment to use, how to use it, and when to use it. Because else you just can't control it. So long duration, over voltage. And by the way, when I say short term and long term, it's based on time than anything else. So the over voltage is still greater than 1.1 per unit, and the under voltage is less than 0.9 per unit. And then you have I think it's Danny who asked me, you have a sustained interruption. This is when we tried opening and closing our breaker at the end, we tried rebooting our system, nothing works. I'm still getting a voltage which is less than 0.1 per unit, which means that there is a dead bird, an animal, a branch that needs to be physically removed. And this is what we call an outage. It's the last thing that we want to do, but then when nothing works, then we just take an outage. The other qualifications that I want you to be aware is stuff that just doesn't fall in the above is harmonics, and we will have an entire thing on harmonics. Notching, noise. So far no one has complained about noise in the voltage, but it's something that we are sort of aware. And DC offset. DC offset is not for regular customers. This is when you have a factory and you're running, you guys DC offset. Danny, can you see that now? DC offset is for very specific customers. It's not for regular customers that they are so concerned about DC offset.
What's the second one?
Notching, Notching.
Never heard of it.
Never heard of that, like, is there an example of that?
It's like a pinching of a voltage. You have a sinusoid and then there is a dip.
What's a notch? Sounds familiar.
Sort of a,
Oh,
for no
it
good
really
reason.
looks-
And noise would similarly be
Yeah, it's-
consistent
so-
sinusoid.
from a sinusoidal point of view, it's like, it doesn't look like a sinusoid. But, and your entire lab 3 is going to be on that, where you don't see a sinusoid and you're getting frustrated, and you later learn that when you add a bunch of different sinusoid, the sine wave itself gets destroyed and it looks really weird. So, I wanted to show you a graph, but before that I think I should go to the last one. For some reason this got flipped, but I didn't want to change it. So let's go to this one. This wouldn't be a part of your exam, but if you're taking higher classes, it's really helpful on how the power world works, and you will always hear it, the word "it depends," and freaks out EITs a lot. EITs are like engineers in training. Freaks out first years. I definitely freaked out. I'm like, I'm not getting a straightforward answer because I'm so used to tell me 10.15 or 10.20, and here's an engineer saying, yeah, it depends. Like, what's the actual situation? So this is one of those graphs which is a depends graph. I'm going to just walk you sort of in a slow pace because I would like you guys to know this, even though you may or may not use it. If you're coming from communications, you might have seen this graph. Anyone from comms? Telephone industry? No one. All right. So let's just go through the X and Y axes first. And this CBMA is a term that we picked up from the telecoms world. So what you have here is a bunch of voltages, but in percentages. So 100% of 100% of the volt is here. What this is telling me is, remember the 1.8 pu and the 0.9 pu that we were talking about? So think of it the same way. So this is like your 0.9 pu, this is 1.1 pu, if I assume this to be 100. So that's how you should understand our unit. The white space is the space where it is safe to operate the device. When we were doing the calculation for the breaker, on the off chance, I believe we spec'd 40 ampere or no, it was a 39.1 and I think I picked a 40 ampere breaker. Yeah, I picked a 40 ampere breaker, but there is a chance that you give 40 amps and the breaker doesn't open. It depends, yeah. What I kept quiet on the other day is the time associated with it. So a breaker opens or closes depending on the energy. So energy is I squared T. So not only should I be concerned with my currents or voltages, I should also be concerned by how much time did I give it to the breaker. So if it was very quick, I can go up to, imagine this to be 100, I can go up to 500. So 5 times what I rated for. So if it was rated for 40, 40 times 5 is 200, 40 times 5 is 200. I could go to 200 amps, but only for so many milliseconds. So this is like 1 millisecond, this is even less than that. Having said that, if I am applying a current that's more than this 100%, let's say 140, the first time that the breaker is going to open is somewhere here, between 10.3 and 10.2. And then any current, so if I have 100% voltage, see this, it's more or less of a white region and I can operate. What I'm trying to drive down here is, it just simply doesn't matter that you had a high voltage. That's not going to kill the system. And that's what I was trying to show you using shooting off this. So that's the stuff that I was trying to drive home by the short term and the long term duration. It also depends on the duration. It's just not that it depends on the voltage alone. And then I go back to my HDMI. All right. So now we can come to some tolerances. So long term duration, it's like 10% over voltage and negative 10 under voltage. Keep in mind, this they are talking from a CBMA tolerance level, not particularly from our world. But the idea is the same. They are telling that, hey, I can go 10% high and 10% low, but I need to be aware that how much time I can sustain that. If I'm going like 400% high, that's no way I can sustain it for 10 seconds. In fact, 400% somewhere here, so that's less than 1 millisecond. And we were talking about 16 milliseconds, so in that case, it's like, it's gone. Don't even think about it. So if you guys were doing the project, there's a trick to doing the project where you have to actually choose a fuse. And in the lab, the fuses are just lying. If you don't read the proper fuse, every day you're just blowing up fuses and not realizing what's happening. You're checking your wiring, you're going to the next guy and asking, and they're coming and checking the wiring, not realizing you picked up the right ampere, but you didn't pick up the right. There's a letter after the fuse which tells you how long it can sustain the time.
Yeah, just look
It's
up.
called literally it's called a fast fuse and a slow fuse. So, depending on the application, what are you trying to do? In a lab, you're trying to get the output. You don't care for PSU's infrastructure, so use a slow fuse. You're working in an industry, you want to protect the equipment, use a fast fuse. And that's the reason for the swell. So swell, like I said, more than 100 is your swell, so it's a bit higher than the expected voltage. So if it was 120 volt, 120 and then add 40%, not 40, probably like 30%, and you can still get away without blowing up the fuse, or it's acceptable to use. Similarly for the frequencies, so the frequency region is this third region that you can have. Oh, there you go. It's not a proper sinusoidal wave. Like on the positive side, you had a bunch of spikes and whatnot, and that's where the frequency comes into play. And you can get away with it for a certain amount of time. Believe it or not, most of your lights, the new ones, although energy efficient, creates this havoc where you have a bunch of frequencies coming in, and I think your lab is based on that. You use a different kinds of, at least it used to be like that. You put a bunch of different lights, and then you measure their spectral activity and you figure out, oh, it's just not 60 hertz. There are different other hertz that are being seen. Similar, the high frequency transient is on, you can have high frequency, but like I said again, when you have a high frequency, pretty sure you're going to see very high voltages, but that's a very tiny, weeny period of time. And of course, voltage sag means the voltage is below the expected voltage. This is an interruption, like the voltage literally collapsed. Looking at this, I'm going to say it's a short-term interruption, not a major outage, because it just happened for so many milliseconds. And even if you go through all this, your equipment is still protected as long as you're operating in this white region. So even if it's on the high frequency side, you're good. If there was an interruption, you're good. If there was a voltage swell, you're good. If there was an under voltage, you're good. But make sure that you operate in the white region. Don't try to operate like 10% of the voltage and keep on operating for 1, 10 or 100 seconds. That's not going to fly.
Would that region damage the equipment? Even though it's in a
Yep.
damaged region?
Yep.
Okay.
So if you're thinking of from the equipment region, yeah, it's going to damage the equipment under voltage.
Would that be a case of it just slowly gets warmer and warmer?
Sorry?
Would it be a case of it can slowly get warmer and warmer?
No. So under voltage, and I can see where this question is coming from. In US, I have never experienced under voltage. Back in India, I've always seen this under voltage happening live. So the big equipments in your homes sort of died down. Like your refrigerator stops, your TV, it definitely stops. The lights, a 100-watt light becomes like almost like a 10-15-watt kind of thing. And you're like, oh man, it's coming. And you just know it's happening. They're about to shut down because they have tried everything and it doesn't work. Most likely that happens when summertime, everyone tries to switch on their AC, and we just don't have enough power to. I think it's now like 1.4 billion people in India. When I left, it was 1.1 or 1.2. I just casually added 200 million people. Did you see that? Like,
You could be right though.
that's the thing with you missing with VA and KVA.
Oh.
It will drive me nuts. For me, 1.3 billion is, 1.3, yeah, it's 1.4. But for US, it's like 100 million people that I just added cash to. So keep in mind your units, don't drive me nuts, please. Yeah, good. And I can assure you, when we were taking this class, we didn't go through this quite in detail because this is covered a whole lot in protections if you're taking that and in advanced protections. But I just thought you should see this. Speaking of which, are you guys all kind of doing analog at this point, analog with digital or EMAG? Or you guys are like, hey, I'm just going to graduate, apply, and see what jobs I get?
Where, do you mean like advanced?
No, so once you graduate, you guys are like, no, I know I'm going to look only for jobs in Intel, Lam, anything to do with analog engineering.
I'm leaving my options open.
Yeah.
Yeah, you are there, right? I think you already are joining right after this. Okay. What about the others? You guys are kind of,
I'm interested in RF.
Okay, got it.
Yeah.
What about Isa? You don't know. Abbas? Got your name right today.
Doing computer engineering, so
Okay.
probably something.
So you are going to be far away. No, you don't have to explain. I just, all right. Reese, you are doing 348, right? Okay. Sorry, I took info, but I didn't give you info. I had a very specific reason to go into power. It had more to do with I wanted to be an EMAG engineer, put in a lot of effort learning. Do you still have that class?
EMAG?
Two terms, yes.
Okay, yeah.
Yeah.
Smith chart and all that jazz, and then one day the professor Rousseff, if he's still around, he's a professor from University of Washington. He had a long chat with me, why am I putting in so much effort in the class? And I said, I want to get a job in this. And he said, are you planning on a master's? I'm like, no, I just want to do this 4 years. And he said, 4 years is not going to cut it. Your master's is just master's with ton of references and papers might get you a job. PhD gets you an entry-level job. That day I don't care for the subject anymore. And then I had to start looking around, and we were doing tracks. So then the next interesting track was analog. We did that for a while, but then I was like, yeah, I don't know whether I want to do this for my entire life. Have you guys taken classes with Richard Campbell?
He
He retired.
He retired?
We
Yeah.
wanted to, but
Oh,
he
okay.
retired.
Anyways, so Richard Campbell said something which just blew my mind away. You can become an analog engineer, you get into an entry level, then you come to a mid-level around 5-6 years. 8th or 10th year, you become a senior engineer. And that's it, that's the end of your life or career. And you're like, what the heck are you talking about? And he talked about a very specific company from Beaverton, and I'm not going to say the company's name. What happens after 10th year in engineering? Well, what happens is after 10th year, there is no position, so to say. 10th year is a cutoff. You already have, if you're in the power, you can jump departments, not so easily on the analog side. So then they make you a manager, and that's you're going to hate your colleagues from day one after that. Because you have to look at their timesheet, you have to show who showed up on time, who was being obnoxious during the Monday check-in. You're driving meetings, and then you're like, wait a minute, I went to school for engineering, what am I doing here? Some cannot wait to become a manager so that they can become a pseudo engineer. Some are like, oh man, this is not the life that I trained for. So 10 years you are doing this engineering stuff, and then you move, even your laptops change. They give you a silly laptop because now all you need is Excel, PowerPoint, and I'm not even kidding. The laptop that I use and the laptop my boss uses are kind of funny. I have a 64 GB RAM, and I'm shouting at him to give me a 128, and he's got like, 16 GB. He's checking his emails, he's looking at his Excel sheet. So just be careful. The easiest way to prep, keep in mind this is going to come. And I can't speak for the international students, but in US, 10 years you're like, yeah, I need to take a break, I need to go hiking, you'll do all kinds of crazy stuff. I believe Intel has a break after 10 years of so many months or a year.
Sabbatical?
Is it like how many months?
Sabbatical,
Yeah.
4 years and 7 years.
Is it at 4 and 7?
Yeah.
Yeah, so 7, you're like, yeah, I've seen enough of engineering now. Hope you guys can still figure out what you want to do, but that's the life, so I didn't want to do that. And then I was like, can I find a, and then there's a risk of layoffs. Used to be every 3 years, now I'm like, I've lost count of how many times I've seen layoffs happening. So I wanted something stable. The pay could be $5,000, $6,000 less. I could care less, as long as I know I have a paycheck coming. And then, this is just me, I didn't want to update myself every 2 years with a new technology. When I was in college, it used to be data science, like everyone was data science hungry. Machine learning was a joke back then, I can tell you, in 2016. There used to be a class where no one showed up. I just checked that class, it's almost full now. And everyone's talking about AI. The good thing about this is you're going to see stuff from in 1970s, in 1960s, and yeah. But things will change. We are seeing a lot of AI entering our field. But at the same time, I was looking for stability, so that was my choice. Once I didn't get my first love, which was eMac, Campbell did a good job of talking me out of analog. I was like, I don't have a whole lot of options here. I mean, what am I going to do? And I was already in my 4th year, so power it was. So I jumped into power, and so far so good. Yeah. So even today it's so stable. I don't think we have had any layoffs, so to say. If you suck at your job, of course you'll get kicked out. Yeah. Bob's going to be mad if he hears why I joined us. Hey, I wanted a stable job, man. Remind me, and if I forget, at the end of this class in June, how do you guys check your salaries? Like, hey, what's a competitive salary? Like, what do you? Anika just woke up. I mean, I was like, whoa. Sorry.
There's this app called Fishbowl too.
I'm sorry, Fishbowl, yeah, Glassdoor, yeah.
Well, Fishbowl's
There's a
the
lady
one,
on
right?
TikTok who walks around the street and, hey, how much do you earn? Right?
A lot of us seniors are talking to each other about our job offers
Okay.
too.
Yeah.
Job offers. I know as a culture in US we don't discuss our salaries, and yet US government has the salary of each and every engineer who came from outside of US. And to get those jobs, you have to be paid more than the US, so to say, your fellow US companion, but that's not how companies do it. They just pay $2, literally $2 a year extra, and that paid more than the expected wages. That is stored under Department of Labor's website. It's a stupid website which no one cares, but I just download it every quarter just to see, am I getting paid enough? If not, hey boss, let's have that chat. And I think at this point he's just so concerned that someday I'm going to send it to everyone in my group. But it's an open document, literally shows you this quarter, and for the first 4 years or so, that's good enough, because it's only at the entry level that we hire folks from outside US, and after that we just stop. So first 4 years, try and refer that. Someone the other day was showing me on Reddit, there was a channel where they post their quarterly salaries, but this spreadsheet is even better than that. But it's a huge file. So it's 85,000 in a year, divide by 4, so around 20,000 lines. So you have to spend a good number of minutes to filter and come up with your number. But that should tell you whether you're being paid fairly or not. In your industry, in your city, in your county, they go to that level. So, yeah. All right.
Department of Labor website.
It's a Department of Labor website. I can send you the link sometime. And if I forget, you have my email ID, just remind me. And
That'll be good.
I'll take care of that. All right. So one of the problems, let's look at the problems due to harmonics. At the base level, to make you understand what a harmonics is, your fundamental frequency is 60 Hertz. Keep in mind I'm talking in terms of US, so this is your fundamental frequency. Harmonics happens when you have multiple of 60 Hertz. So in your current or voltage, you will have multiples of 60 Hertz showing up. What that looks like is, so for example, you have, I think I'm coming up with that. Just give me a second. So not only is it 60 Hertz, it has to be the odd multiple of 60 Hertz. So 60 times 3, 60 times 5, 60 times 7, you get the idea. So 180 Hertz would be there. This is what, 300 Hertz, am I right?
Yes.
And this is 36, 540 or 480? That is like 420, sorry.
420. Yeah.
So 420 Hertz. What happens is, if you have the odd ones and the even ones also do show up. But what happens with the even ones are that they cancel out each other. What I mean by them cancelling out each other, you have three-phase power, right? So VA, this is 120, let me just, 360. So let's take the case of 120 Hertz. What happens with 120 Hertz is, you would end up with VA, let's say, no, that's not the way I want to explain. Oh yeah. So we started this class with VA 0 degree, VB negative 120, VC positive 120 degree. What happens for the even ones, when I add the voltages or current, my neutral would be 0. What that means is IA magnitude, IB. Sorry. Would be I neutral. That's not going to be the case in case for the odd ones, your odd frequency. You will, and I can show you a very short derivation. What happens is, and if this is the case, let's just continue on this even thing. And if this is the case, if I add IA, IB, and IC, my neutral current, because it's a perfectly balanced system, would be 0 amperes. That's not the case in odd. And I'll show you the derivation. What happens is your I neutral is actually 3 times one of these currents. So let's just pick IA. This causes a lot of headache, because earlier I was showing you, and there was I'm not sure whether it was an email or a Discord talking about 3 wires and 4 wires. And at the end of last lecture, I was saying, no matter what, expect your client to have the 4th wire in the neutral. Never leave it to them to do the right thing. They will never do it. expect them to have a fourth wire. And the fourth wire is because there is going to be a neutral current, and that neutral current is going to be 3 times, I'm just picking this as IA for now, 3 times IA. And we just did a wire sizing calculation. So if you end up with 50 amps for your phase current, don't just blindly pick 50 amp for your neutral. You actually have to go 3 times the phase current for your neutral. So one issue with the harmonics is this frequency that's going to cause a lot of trouble. And next class, when I am actually getting into very much into the harmonics, you will have slides and I'll go through the derivations. Most likely I'll do it today, but just in case. So that's one issue. The second issue is, and this is more of any AC conductor that you can think of, it's called skin effect. Yeah. Did you get to walk around the lab and see all the stuff that's there, just in case? Yeah, okay, some stuff, yeah. So, any conductor that you see on the roads or next to your house that's owned by one of your power utilities, PG or Pacifico, you would see some sort of a big conductor like A, and it would be twisted. Like, you could see, if you zoom in properly, you could see that it's just not one strand of cable or wire, it's several strands that are twisted together. The skin effect is a property where AC current actually likes to flow through the surface of the conductor. So this would be, and I don't have great 3D skills, but let's see what I can do. So this is one conductor in that bunch of those conductors. How should I explain? So this is like one particular, I think it's like, what's the gauge? 1500 NCM is what we call, and this is just one aluminum wire that we twist and we come up with this. The trouble with AC current, and it's called skin effect, is higher the frequency, more the current wants to travel through the surface rather than through the entire surface. And we don't have this issue in DC. This is also a reason why we try to do high voltage DC, because high voltage DC, I can pretty much use the entire surface here. AC on the other hand, it's trying to push itself and occupy only the outside. Now with harmonics, the other issue is it's got multiple frequencies, right? So low density current flows or tries to occupy the inner rings, whereas the high density or the high frequency, high density current that didn't jive. So the high density currents try to occupy the outer. So there is always this issue that you have different frequencies trying to fight for the conductor, and then higher the high density, you have to come up with larger conductors, and that again is a high cost option for us, and we try to avoid that. That's the reason we are so concerned about power quality. So in a proper world, we would like to get away with harmonics, but the fact of the matter is similar to power factor. Once there is harmonics in the system, we just find different ways to get or compensate for it. There is no real way to get rid of harmonics. Unless you have a very good customer who's willing to pay you a lot of money, there is no way that you can get out of it.
Question. Low density what?
Low density current and high density current. lower the density or even low frequency and high frequency. I would even go with low frequency and high frequency.
Kind of the higher the frequency, the more it wants to flow on the skin.
On the skin, and that's called the skin effect.
The higher the frequency?
The more the current wants to flow on the skin.
Yeah, around voltage. Thanks.
You guys want to take a 5 and then come back?
Boy, this stuff is scary.
Is there a Paul Robertson in this class?
I think it was Drew.
Okay.
Yeah,
Aw.
he was in our group.
Oh, I was gonna say, I think we had Edith.
Yeah, but he was Drew from this class. He was here. He was in our group.
Oh, that was
Yeah, yeah, in our group for this class.
Yeah.
Yeah, rest up.